Okay, so I think we're going to be able to finish the review for the final today. That means Thursday will be kind of a tutorial day. And I'll just zoom in from my office in case you have questions. And then we'll meet on the Tuesday, the 12th for the final. You can take it here or you can take it in Brightspace, whichever you prefer. Okay, so let me see. I had marked, we were up to number 29, I think, was the next one on the list. And I don't have any marked in yellow, so I must be doing all of them. Was that what I was doing? Yeah, okay. Yeah. My memory doesn't go back that far. Okay, so let's pick up 29. Which of the following contains the strongest bond? Okay, what we're into now, with the strength of these bonds, since they're, you see, these are ions of dinitrogen. So we can't answer those questions with valence bond theory because they all have triple bonds. They just have those extra electrons. So the only way to ascertain the strength of the bond is to go to the molecular orbital theory. Right. Okay, so nitrogen is going to be, it's going to have sp mixing. So if we start with that one, that's the first one, right? Yeah. Let's do this. A, B, C, D, and E. If we start with the first one, let's just put them all up here first. Into minus, 2 minus, and then into plus, and into 2 plus. Okay, we're going to have our we're not going to put the 1s's up here. We're going to start with the valence shell. So we'll have, for the valence shell, we're going to have sigma with the 2 s's, sigma star with the 2 s's. Then when we get to the p's, normally without mixing we would have sigma 2p, but since it's mixing, we'll start with pi 2p, and then we'll do sigma 2p. Then we'll do pi star 2p, I think. Yeah, pi star 2p, and then if we need it, it'd be sigma star 2p. Okay, so the number of electrons is where we want to go next. So we're talking about valence electrons only. That means 10 here. And 1 extra one would be 11, 2 extra would be 12, 1 less would be 9, and 2 less would be 8. So that's the number of valence electrons that have to go into those shells. Excuse me. Okay, so we can put 2 in the sigmas, 2 in the sigma stars. We can put 4 in this one, which would be 8. Then we have 2 more. There we go. Okay, so the strength of the bond depends on the bond order. And if we calculate the bond orders over here, we have bonding, bonding, and bonding. So that's 8 minus 2 antibonding divided by 2, which is equal to 3. So the bond order for this one is 3. All right. If we put 1 extra, I'm just going to put 2, 2, 4. That was full. So the next one goes into an anti-bonding orbital. It means we have the same number of bonding, but we have 1 extra anti-bonding. So that decreases this one by half. Right? It weakens the bond. Similarly, if we add 2 electrons, the second one also goes into an anti-bonding orbital. That makes 8 minus 4 over 2, which is equal to 2. So now it only has the strength of a double bond. If we subtract 1, then we would do this one would be out to here, would be 2, 2, 4, and instead of 2, We took one away, so that's 1. So now we have this one, and we're -1 from the bonding. So it's 7 minus 2 over 2, which is also 2.5. And this is 2, 2, 4, and we're missing another one there, which is 6 minus 2 over 2 equals 2. Right. So the strongest bond is still going to be this one. The neutral dinitrogen molecule has the strongest bond of all of them. The reason that we had trouble with these two is because the electrons were being added to antibonding orbitals. And the reason we have trouble with these two is because we were subtracting electrons from bonding orbitals. So either one will weaken the bond. Add to antibonding, subtract from bonding.
What did the stars? The stars are the
Antibonding. Yeah. Bonding, antibonding. Bonding, bonding, anti-anti. This is, and these, if with SP mixing, the pi comes first, but without SP mixing would be oxygen and fluorine would fit that model. Then the sigmas come first. I don't think it would, even without SP mixing, we'd still get the same results. Because you still have the antibonding here, and bondings are just, doesn't matter really. Okay, number 30. Okay, equal masses of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? All right, so when we're reacting hydrogen and oxygen gas, we're basing our stoichiometry on this reaction. Forms water. And let's see, we need 2 oxygens here, and that means 4 hydrogens. So that's the balanced equation. If we have equal masses of hydrogen and oxygen gas, so we have X grams here and we have X grams there, exactly the same. Oxygen is 32 grams per mole, and hydrogen would be 2.02 grams per mole. Okay, if they have equal masses, say we have 1 mole of oxygen, right? Then we need 2 moles of hydrogen, but 2 moles of hydrogen is only 4 grams. Say if 1 mole, then 32 grams, right? So if they're equal masses, then this would be 32 grams also, correct? Okay, if that's 32 grams, that's 16 moles. So oxygen is limiting. Okay, that's why A is the best answer. Hydrogen is not limiting. Water can't be limiting because it's a product. Nothing is limiting, it's just dumb. More information is needed, I'm just running out of options. So oxygen is limiting, if that makes sense. Yeah. Because our stoichiometry is based on moles. 1 mole of this would be 32 grams. If we had equal masses, 32 grams over here would be how many moles? Well, we would only need 2 moles or 4 grams, right? So minus 4 grams would equal to 28 grams excess, right? So you can look at it this way, or you can look at it that way. Hydrogen is still excess and oxygen is limiting. All right, 31. Let's see, 45.9 gram sample of metal is heated to 95.2 and then placed in a calorimeter. Okay, we're talking about thermochemistry here. Containing 120 grams of water at 21.6. The final temperature of the water is 24.5. What metal is used? Okay, the question is, what's the metal? And the only way we can define the metal, since we don't know the number of protons, we have to go with molar mass. And molar mass, and put it over here, molecular weight, that's the way I say it, is mass and the number of moles that represent that mass. So a 45.9 gram sample of metal, we're given the mass, 45.9 grams. What we're after is the number of moles. Okay, so if this is a thermochemistry problem, then we need to set it up like this. We're given nothing about the calorimeter. So we're not going to have a term for that one. Remember, everything has to be equal to 0 in a calorimeter. When we add everything together, all the heat changes. So we have the heat change for the water, and then we have the heat change for the metal. Like that. That's it. If we knew anything about calorimeter, then it would be another term. Okay. So how does this expand? Well, we have the mass of the water, right, times the specific heat of the water, times the change in temperature for the water. That represents this value right here. Okay, and same thing for the metal. We have the mass of the metal, we have the specific heat for the metal, and we have change in temperature for the metal. All right, so what are we given? We're given the mass of the metal. Got that right here. Put them over here. Mass of the metal equals 45.9 grams. Okay, we're not given, well, the mass of the water, we're given that one. Let's put what we do know. It's 120 grams. Okay. The temperature of the initial temperature of the metal is 95.2 degrees. So the temperature initial for the metal is 95.2 degrees C. The initial temperature for the water is 21.6 degrees C. Let's see, final temperature will be the same for both of them. And that was given as 24.5. See. Okay, what else are we given? Specific heat of water, 4.18 joules per gram degree C. That's for water. This we don't know. That's our unknown. Okay. The change in temperature will be final minus initial. So the final temperature for water is 24.5 minus the initial temperature for water, which is 21.6. I'm going to have to spread things out a little more. And the mass of the water is 120 grams. Okay, so grams cancel, temperature cancels, and leaves us with joules. Right? Yep. Okay. So this gives us a heat term. This is the Q term for water. This mass here for a metal is 45.9 grams. Specific heat, we don't know that. Final temperature is still 24.5. and minus the initial temperature, which is 95.2 degrees C. Okay, so we can find out what the we can find out what this term is, this right here. What will that tell us? Specific heat is joules per gram degrees C. Now, okay. I was barking up the wrong tree. We're not going to be able to calculate molecular weight because we can't do moles. But we are given specific heats for the different metals. You probably saw that already. Different specific heats. So when we determine the specific heat, we can compare it to our possibilities and see which one fits closest. So that really is the answer we're looking for. This one will give us the metal. Okay, what's this one? Let's see. You didn't bring your calculator? Okay. 120 and 4.18. And this one is 24.5 minus 21.6, which is 2.9. And that's times this. Okay, so this whole thing together is 1,454.6 joules. Great precision, yeah. I'm keeping decimals so I can avoid rounding error. This 24.5 minus 95.2 is minus 70.7 for that times 45.9, yes. Okay, and this is minus 3245.1 times that. Okay, and that's all equal to 0. So if I move this one over on this side of equals, that'll make it positive. See, that should be just a capital M, a metal. There we go. And I moved it on this side, so that means this is left over here. 6. And this would be then that number divided by this number. See, they're in my calculator. So I just hit divide. And this is going to be 0.448 joules per gram degree C. 448. 448. Closest one is iron. Right, rounded off. So this should be iron. Okay. All right. 32. Nitric acid was first prepared to, okay, there's a lot of fluff in this one. A lot of blue smoke. Let's see. Nitric acid was prepared by that reaction. Sodium nitrate, saltpeter plus sulfuric acid, and it produces sodium hydrogen sulfate plus HNO3 gas. And then the gas was captured and condensed, or it was either condensed or it was distilled over with water. Okay, so calculate the delta H for this reaction, for this balanced reaction. Is it balanced? Let me check. 1 sodium, yeah, okay. Nitrate didn't change on either side. Okay, nitrate. 2 two hydrogens. There's one with the nitric acid and one with the HSO4 and so forth. Yeah, it's balanced. Okay. So how do we calculate the delta H for this reaction? Heats of formation. Products minus reactants. Right? So we have 1 mole of each, so we can go ahead and use the straight values. This is going to be, right, these are the products. So the product is NaHSO4 would be minus 1125.5. 1125.5 kilojoules. Since there's only 1 mole, I'm just going to leave it at that. And then we're going to add H2SO4, right? No, HNO3 products first. Minus 135.1 kilojoules. And then we subtract sodium nitrate, minus 467.8 kilojoules. And then H2SO4 was minus 814. Minus 814 kilojoules. Okay. So let's see. What do we get here? 1125.5 and 135.1. This is minus 1260.6 kilojoules. And this side, 467.8, 814. This is minus 1281.8. Okay. This negative is going to make that a positive. So then we just put those together. Let's see. Let's change that sign. Put that, make that a negative. And add them together. Okay. So I get 21.2 kilojoules. Okay. This is products. This is reactants. Right. Oh, there it is. Yeah. Now we'll go to short answers. Okay. Complete the following table. This is 33. So we've got number of protons, number of neutrons, number of electrons. And then atomic number, let's see, that would be, use the right terminology, Z. And mass number would be A. And net charge. Okay. So we're starting off with 55 manganese, 3 plus. Yep. Okay. Net charge is obvious. It's 3 plus. Mass number is 55. Okay. Atomic number and number of protons is the same. We just look that up. 25. Okay. Neutrons would be 55 minus 25, right? Is 30. Right? And number of electrons. Well, we have an excess of positives, so we had to lose 3 electrons. So to lose 3 electrons, we need 22 of them. Okay. All right. And a little nomenclature here. Excuse me. 34. A, B, C, D, and E. All right. If we have FeSO4, the first thing you ask yourself is there a metal in this compound? Yeah. So it's either a type 1 or a type 2. Type 1s are fixed charge. Iron's not a fixed charge, so it has to be a type 2. Now, that means we have to figure out what the charge is. Sulfate is a polyatomic ion with a 2- charge. So this iron must be +2. That means we would say iron 2 sulfate. That would be it. Unambiguous, non-redundant. Next one, sodium C2H3O2. Sodium C2H3O2. You have to recognize this as the acetate ion, which means it's a -1 charge. And you can look it up in your table if you don't remember. This is an alkali metal, which is a +1 only. That's it. So all we have to say here is just sodium acetate. No need to put the charge in there because it's fixed. Also for this one, silver is a fixed charge. It's a transition metal, yeah, but it only has one charge possible. That's a +1. So all we have to say is silver chloride. That does it. Next one, CaSO4. Here we have the sulfate again, and that makes this one +2. But calcium is an alkaline earth, and all of those elements are fixed charge when they're ionic compounds, right? We're not talking about oxidation states. So all we have to do here is just say calcium sulfate. Okay. And this one, N2O3, is it? Yeah. This one is a non-metal. These are all metals and non-metals or metal polyatomic ions. So they would be 1s or 2s. This would be a type 3. So for a type 3, we have to say just how many there are. Dinitrogen trioxide. That's it. Okay. Let's see, 35. Let's see, does 35 bleed over? No, it's just those two in 35. Okay, write the formula for aluminum hydroxide. Okay, we can tell from the name that aluminum is a fixed charge, but we should already know that anyway. Aluminum hydroxide. Aluminum, then hydroxide is a polyatomic. This is a 3+, this is a -1. So we have to have 3 of those. And we can't change these subscripts because that's a polyatomic ion. It functions as a single unit. So single units must be surrounded by parentheses before you can subscript. The next one, sulfurous acid. All right. Since it doesn't start with hydro, we know that there's oxygen involved. Well, uses are derived from ites. Ites become uses. So instead of, if it was sulfuric, then it would be from X, right? X give us, let's see, wait a minute. X should be up here. X are derived from not ith, but 8. So this would be sulfuric acid. This would be sulfurous, SO2. This is ite, sulfite, sulfate. 8 gives X and ites give us us's. So H and then SO3. With a 2 minus, we need 2 of these because hydrogens are +1. H2SO3. Now, it only asks you for the formula. Just remember that this would have to be an aqueous solution in order to be called an acid. If it weren't an acid, then we would say hydrogen sulfide. Okay, let's see here. Got that one worked out down here? Yeah. Okay, 36. Consider the following data. Okay, so these are balanced equations with their enthalpies. And we're supposed to use Hess's law to find the change in enthalpy for the following equation. Okay, so this is what I call our target equation. Calcium carbide, that should be a solid. Yeah, and water. 2 waters. Yields calcium hydroxide in an aqueous solution and acetylene gas. Okay, that's what coal miners used to use in their lanterns. They would put these crystals of calcium carbide in their lamps on their heads, and then they just add a little bit of water to it, and then they hit it with a spark, and you get a light. I don't think it produced much light, right? But that was the least of their problems. What it was an open flame in a coal mine that could have coal dust or methane. And that's why they stopped using them. Too many explosions. Okay, that's our target equation. So how are we going to get there? Well, we want to account for each one of these reactants. And then if we have to use a component reaction that has added compounds or elements that we don't need, then along the way, those have to cancel out. So let's start with calcium carbide. Which one's calcium carbide? The top one, only it's in the wrong direction. There's one calcium carbide here and one there, but we do have to flip it. So this one's going to be calcium carbide yields calcium solid plus 2 carbons, and this is graphite. And the value there would be, we change the sign on our enthalpy because we flipped the equation. So this is plus 62.8 kilojoules. Okay, takes care of this one. But we've added a couple there that we eventually have to get rid of. How about calcium hydroxide? Let's stick with the calcium spurting. Calcium hydroxide. I see the third one down as calcium hydroxide. It's on the correct side with the correct moles. So this is going to be calcium oxide and water, right? Yields calcium hydroxide. And that value is as is, minus 653.1. Okay. That takes care of this one. And it gives us one of those. All right. How about acetylene? Acetylene comes along at the fourth one. Acetylene's on the wrong side. We need acetylene on the right side. That's on the left side. So we're going to flip that equation. So on this side, we're going to have two CO2s plus water. There's our other water. And then the acetylene. Let's put the acetylene over here. Oops, that's too far over. C2H2 gas. And then five halves oxygen. Now, okay. That value would have to change the sign. All right. So the sign is negative. It's going to be positive now. Plus 1300. Okay. That takes care of acetylene and both of our waters. Okay. So now we must have some terms in here. This one, that one, and this one, and this one. Okay. So we've still got calcium. Yeah. We've still got the second one and the last one that we can work with. All right. The second one has calcium on the left-hand side, which in our case is what we need. We need calcium on this side to cancel it. All right, so we'll leave it like it is. Calcium solid plus a half oxygen. Yields what? Calcium oxide. And that value then would be minus 635.5. Okay. So that cancels calcium, right? Cancels calcium. We'll hold on the oxygen because there's more than one. And this one cancels that one. That. Okay. So what do we got left? Let's see. Graphite. The last one. Graphite will be on this side so that it'll cancel. So we'll write it exactly as it is. Plus O2. Graphite plus 1 O2 yields CO2. Okay, and that value would be minus 393.51. 3.51. Okay, CO2. Well, let's see. Now, we need two of them. So we need to multiply this by 2. The whole thing by 2, actually. So that's, 2 here, 2 there, 2 there, and let's see. 2, 1 and 6 is 7, 18, 1 and 6 is 7. So this is going to be, we use this one, that one, that one, that one, and that one to add up. Now, this 2 graphite, yes, that cancels. 2 is 4 halves, right? So 4 halves and 1 half is 5 halves. So 5 halves here, those are gone. 2 CO2s, it's gone. Okay, let's see if we got everything. Those are canceled. We got the waters. We got the calcium carbides, we got the calcium hydroxide, and we got the acetylene. That's good. So now we just need to add our numbers. 62.8. 653.1 is subtracted. 1300 is added. 635.5 is subtracted, and 787.02 is subtracted. So I get delta H0 for this reaction as two places, minus 712.8 kilojoules. 713. Okay. These Hess's law problems, you've really got to be methodical about putting things together and checking them off. Otherwise, they can be messy in a hurry. Okay, 37. Which of the following has the largest first ionization energy? Sodium or rubidium? First ionization energy. Which one's larger? Well, let's look. Where are they on the periodic table? Sodium ionization energies, they increase what? From lower left to upper right, correct? And they increase from bottom to top or from left to right. Sodium and rubidium are in the same group. So rubidium is going to be the lowest, sodium is going to be the highest. Okay. All right, 38. Let's see, which of the following has the largest atomic radius? NO. Radius. Okay, we're not making ions out of them. We're just saying, as atoms, which one has the largest radius? All right, the radius increases from upper right to lower left. Now the radius increases going down, it increases going left. It increases going left because you're decreasing the nuclear charge. It increases going from top to bottom because you're adding energy levels to your electrons. So nitrogen and oxygen, they're in the same period. Oxygen would be smaller than nitrogen. So the question was, which is the largest? Nitrogen. All right. Oh, okay. We get some hybridization going on in here. Consider the structure of glycine, the simplest amino acid. All right. We've got two carbons. And we've got NH2. Got hydrogen, hydrogen. And this is C with a O and then a OH, correct? Yeah. If you ever run across this again, this is the alpha carbon. For amino acids, that's the one around which everything revolves. You'll always have one hydrogen on that alpha. And this is the R group, right? In glycine, the R group is hydrogen. It could be other things. Alanine would be a CH3 group, for instance. So this one would change with the amino acid. But all of this would be exactly the same. You'd have an amine group here and a carboxylic acid group there. And this is the only one that changes for the amino acids, in case you ever run across them again. Okay, now the question is, let's see, if this is 1, this is labeled 1 and this is labeled 2. Indicate the hybridization of each nitrogen and carbon atom. Okay, so we've got carbon, carbon, and nitrogen. All right, we need to break this one apart. Here's what this one looks like. Hydrogen, hydrogen, and a lone pair. That's the trick to this one, recognizing that that nitrogen has a lone pair on it. It's kind of like ammonia, right? With its lone pair. Nitrogen typically has 3 bonds with its lone pair. Now it can have 4 bonds. If we put another hydrogen up here, right, then that would make it ammonium. Right? But in this case, it's got 3 bonds to it, 1 lone pair. So now we can say something about hybridization. This one has 1, 2, 3 equivalent bonds. Right? So C1 is sp2, 1, 2, 3. Okay. The second one has 4 bonds to it, so it's sp3. And the nitrogen has 1, 2, 3, 4 groups around the nitrogen, which is sp3. And that lone pair occupies one of these hybrid orbitals. All right. Oh, I forgot. How many bonds are in the molecule? Okay, well, let's see if we count them up. There's a bond. How many bonds are in the molecule? Okay, total bonds. All right, we've got 1 between the hydrogen and oxygen, carbon, oxygen. Double bond to the oxygen is 2 more. Then between the carbons, then 2 hydrogens, right? Then 1 with the nitrogen, and then 2 more. That's 11. Oh, wait a minute. Okay, it's counting the double bond as 1 bond. Okay, so we only have 10. I was counting the sigma and the pi separately, but if we count it as just a double bond, then we only have 10. 10 bonds. And 1 pi bond. All right. Oh, we're getting back into multiple choice. 40. Gave us a short break. You're holding 2 balloons, orange balloon, blue balloon. The orange balloon is filled with neon. This one has neon in it. And the blue balloon has argon in it. I don't know about their sizes yet. The orange balloon has twice the volume. Okay, so the orange balloon, this one, has twice the volume of the argon. All right, so this volume is twice the volume of the argon. All right, we're given that. Let's see. Which represents the mass ratio of neon to argon. All right. If this one is twice as big as that one, that means the number of moles of neon is twice the number of moles of argon. Okay. All right. So, if we say, let's see, how should I approach this? It might make more sense if I just give them numbers. Right? If I say, all right, what does that mean? If this is 1 mole, then this has to be 2 moles, right? Because it's twice that. All right, if this is 1 mole of argon, how much does that weigh? Well, let's see. Argon is about 40. About 40 grams. 2 moles of neon. Neon is about 20. So 2 times 20 is about 40 grams. So they have the same mass. The ratio is 1 to 1. That works better than any I've tried to explain in the past, doing it that way. I think Einstein would approve. He was big on thought problems and reality. 41. Which of the following electron configurations is different from that expected? Okay. So let's see, we have A, B, C, D, and E. Yep. Okay. We've got calcium, scandium, titanium, vanadium, and chromium. All right. The only ones that we've discussed in terms of anomalies, the electronic configurations are those that occur in the middle of a period. Calcium is way over there on the left. I mean, it has a 4s2 as its final, right? It would be argon 18 and then a 4s2. That's exactly what we'd expect. Scandium is like calcium. It's right next door to calcium. So it would be argon 18. It would also have 4s2, but it would have a 3d1. All right. Just need one more electron. Titanium is like scandium, only it has another d electron. Right? When you think of where do they go? Well, these go like that, and like that. They're paired. This one has 5 possibilities. Right? And with one, that it only has that choice. This one would be like that, right? Because of Hund's rule. You can't pair them up until you get all the way across, and then you can start pairing them up. Vanadium as another one. Right? So vanadium has the 4s2 and it has 3d3. 2, 3, 4, 5, 2, 3, like that. That's exactly what we expect. Chromium. All right, we're going to add another one with chromium. All right, so it's 4s2, 3d4, right? That's what we would expect. Here's the problem. Quantum mechanics tells us that it's more stable to have a half-filled orbital than it is to leave one dangling like that. When you're that close to getting half-filled, then it's more energy efficient. It's a lower energy to take one from here and put it over here. So chromium is the one that we don't expect to be that way by our simple rules. Now, the equations that are used to generate these electronic configurations in quantum mechanics will tell you that that's right. That's what it is. But we're not that deep into their math, so we have to say that's an anomaly. The same would be true if you're one electron away from a complete 3D orbital. And where would you see that? copper. Copper would steal one of those s electrons to complete its d orbital, make 10 electrons in the d orbital, and leave one in the 4s. Let's see, 42. Oh, how we doing on time? Oh, we're good. Let's see, 42. Choose the molecule with the strongest bond. Strongest. Okay. Let's see. A, B, C, D, and E. I think this one's methane, right? Yeah, and then water. And NH3 and HF. And then they're all equal. All right. What determines the strength of a bond? Well, there are a couple of factors. One is, well, we don't have any ionic compounds in there, so we don't have to worry about that. But we still have to consider electronegativities. The electronegativity differences are not that far for carbon, hydrogen and oxygen, nitrogen and oxygen. Fluorine, right, we're working our way across carbon, nitrogen, oxygen, fluorine, from left to right in that second period. So we're gradually increasing the electronegativity of the non-hydrogen. So that's one of the things, electronegativity difference. Okay. So in that case, this would win because that electronegativity is different. The other difference is how is the bonding being shared, right? Here we're sharing it with 4 bonds, like we're splitting that electronegativity difference with 4 bonds. Here we're with 2, here with 3. Here it's all owed to that 1. So I would say if we looked up the values in a reference manual, we would find that the bond energies in here between the central atom and any of these hydrogens would be greatest for HF. Now, did I? No, I didn't do a work problems for this one. Okay. So that explanation will have to stand. All right. Let's see, next. Yeah. 43. Three samples of a solid substance composed of elements A and Z were prepared. The first contains 4.31 grams of A and 7.70 grams of Z. The second is 35.9% and 64.1%. It was observed that 0.718 grams of A reacted with zinc to form 2 grams of the third sample. Show how these are the law of definite proportions. All right. When we're talking about the law of definite proportions, I think that was Dalton. Anyway, what is that saying? That's saying that for any compound, the mass ratios of elements in the compound is constant, regardless of the source of the compound. It could be isolated from nature. It could be the product of a chemical reaction. Doesn't matter. It's going to have the same proportions no matter where it comes from. So how would we demonstrate this? Well, if we had the ratio of A to Z or Z to A, I would do Z to A because Z is heavier, right? It's 7.7 grams versus 4.31 grams. So sample 1, 2, and 3, let's see how we would deal with those. Right, the Z to A mass ratio would be simple to calculate for that first one. 7.70 divided by 4.31. All right, so that's going to be 7.7 and 4.31 is 1.79. Three significant figures. Okay. So how about number 2? Number 2 is 35.9% A and 64.1% C. Well, if that's mass ratio, we can do like this. Just assume you have a 100-gram sample, right? If you have a 100-gram sample, then 64.1 grams of it would be Z, and 35.9% grams would be A. 64.1 and 35.9 grams. That would be 1.79. Same ratio. Okay, how about the last one? Let's see. 0.718 grams of A reacted with zinc, with Z to form 2 grams of this third sample. All right, the total mass here is 2 grams. Right, so A is 0.718. 0.718 grams of A, and Z would be the difference. It would be 2 minus this. Correct? Okay. Because this is a total. This is what A went into it, and what's left over is Z. So we need 2 minus 0.718, which is 1.282. So it's 1.282 divided by 0.718. 718. And that's 1.79. Same ratio for all of them. That is a demonstration of the law of definite proportions. That ratio is the same no matter what type of experiment we encounter or how we analyze it. Now, the original law was for mass. But we could do the same thing for moles, right? If we had the mole ratio, whatever the source is, we could say, all right, water's mole ratio of 2 hydrogens for 1 oxygen. If this were distilled, right, from salt water. But if we reacted and produced H2O from hydrogen plus oxygen, right, be the same thing. Same mole ratio, same mass ratio. So now we know that the mole ratio works just as well as the mass ratio. But originally, they didn't know that.
So that law, all 3, no matter what, are going to be like the same?
They're being the same. Yep.
Okay.
If we're talking about the same compound, let's see. 3 samples of a solid substance composed of elements A and Z were prepared. Okay, what we're proving is that it's the same compound because it's the same ratio of Z to A. 44. Okay, for 44, write the balanced combustion reaction for C2H5OH. We know that this is one of the reactants, C2H5OH. If it's combusted, the other reactant has to be oxygen. And what do we get when we combust a carbohydrate like that? You always get, if it's complete combustion, you always get carbon dioxide and water. You have to know that or you can't complete the answer. Now we can balance it. Okay. I could probably do this freehand, but let's do it with the budget method, just for practice. Carbon, hydrogen, and oxygen. So we have 2 carbons. We have 6 hydrogens, and we have 3 oxygens. On this side, we have 1 carbon. We have hydrogens, 2 hydrogens, and 3 oxygens. Okay. Where do we start? Well, we don't start with oxygen, right? Because it's a single element. Right? We'll save that to last. Besides, it's already balanced. We're going to throw it out of balance in a minute, but we're going to leave it till last. So I would go to carbon first. All right, we need 2 carbons on this side. That's 2 there. That means 4 plus 1 is 5 oxygens. Okay. Now we go to hydrogens. So we have 6 hydrogens on this side. If we put a 3 here, that makes 6 hydrogens. Okay. But now let's have 4 plus 3 is 7. Right. 7 oxygens. Okay. How do we get 7 oxygens on this side? Well, we already got 1 right there. So we really only need 6 out of this one. So a 3 here will give us 7 total. Okay. That's our balanced equation. And we can see immediately that it's good. All right. Anything else? Oh, yeah, we got another one. 45. Let's see. Photogray lenses incorporate small amounts of silver chloride in the glass. The following reaction occurs in the light, causing the lens to darken. So we go from silver chloride, which is colorless, to silver ions, which are gray. They are able to absorb light. Okay. The enthalpy change for this reaction is 3.1 times 10 to the second kilojoules per mole. Assuming all the energy is supplied by the light, what is the maximum wavelength of light that can cause this reaction? What we're saying by maximum wavelength is any wavelength that's longer than that won't have enough energy. Do we need that or shorter wavelength? So if this reaction for each mole of silver, we need 3.10 times 10 to the second kilojoules per mole. What did I say? 3.10 times 10, we're at kilojoules per mole. And I would say mole of silver. Okay. All right. If we're going to equate this to some wavelength, we've got to use one of these equations, right? We know that, excuse me, we may not need it, but we do know this, that lambda times nu is the speed of light. We also know that Planck's constant times the nu equals the energy. And we also know that if we solve this for that, then we have Planck's constant times c over lambda. So that's what we're getting at. We want that wavelength. But this is in kilojoules. We need joules. All right. So if we take this one and we go, all right, this is per mole. We want per molecule or per atom, right, of silver. Right, so what we have to do is we got to get rid of the moles first. Well, we could get rid of the kilojoules first, but let's do the moles first. So the mole of silver ions is atoms or ions. Yeah, let's be consistent. I put an ion up there, so it's ions. So 1 mole is 6.022 times 10 to the 23rd ions per mole. Yeah, that gets rid of moles. So that's this kilojoules per ion. Now we can change it to joules because joules is the standard unit of measure for energy, not kilojoules. So if we have kilojoules down here and joules up here, it's 1,000 joules per kilojoule. That gets rid of that one. So now what that does is that says this is joules per ion or joules per atom of silver. That gives us the energy for just one transition from silver chloride to free silver chloride atoms. So this is silver chloride solid, right? Silver chloride solid. It's ionic right there. But what we're going to do is put enough energy in there to split those ions into separate ions. Okay. We're breaking an ionic bond there. Okay. Let's see. 3.1 exponent 2 divided by 6.022 exponent 23 and then 1,000. So that gives us 5.148 times 10 to the minus 19 joules per ion. All right. That would be this energy right here. If we want to solve for that wavelength, bring it over here, Planck's constant times C divided by energy. Right. Keep this one and this one here, bring this one over here, bring that one over here. So I need Planck's constant. Is it up there? 6.626 times 10 to the minus 23, 34. 6.626 times 10 to the minus 34 joules seconds. I'm going to hang on to units just so it can keep me honest. And speed of light is 2.9979 times 10 to the 8th meters per second. So seconds are going to cancel. And then energy is 5.148 times 10 to the minus 19th joules, right, per ion. So that cancels joules. That leaves us with meters, and that's wavelengths in meters. Right. We'll deal with the units in just a minute. So let's take, see that one, and then I want 2.9979 exponent 8. I want to flip those and divide by that. And then 6.626 exponent minus 34 times. So this is 386 times 3.86 times 10 to the minus 7th meters. And that would be a valid answer. And it didn't ask us, it didn't tell us the units, so that would work. If we put it in nanometers, well, a nanometer is 10 to the minus 9th meters. So if I make this one bigger, that one gets smaller by 2 powers of 10. So it'd be 386 times 10 to the minus 9th meters, right? Okay, this is a nano. So that's nanometers, 386 nanometers. Okay. All right. Let's see what we got here. Oh, this one looks familiar. think we've seen this one before. And I left all my colored markers in the office. Okay, 46. So we got this table with hybridization and then electronic geometry and then bond angle. Do like that. Then we got 3 places here. There we go. This is A, B, and C. And the only thing we're given is this one, sp3 hybridization for this A molecule. Okay. Molecule B has 2 more effective pairs. If it has 2 more effective pairs than this one, then we have to get them from the D's. Right? 2 more fixes. Molecule C consists of a sigma bond and 2 pi bonds. The only way you can get a pi bond is if you've already got a sigma bond. So if you've only got 1 sigma bond, then those 2 pi bonds must be between 2 atoms. And it's no other choice. So this hybridization has to be sp. It's a linear molecule. So that's linear. This is octahedral, right? 3, 4, 5, 6. And this one is tetrahedral. Okay. So the bond angles here, the electronic angles, bond angles would be 109.5 if every position was occupied by an atom. You had a bond. We have to assume that, otherwise there's no reason for it. This one, the octahedral, is going to have something like that, something in the middle, and you can have a 180 degree here between these two, or you can have 90 here, 90 here, 90s all around this square, or 90s like that. So it's 90 degrees and 180 degrees possible. And this one, there's no other possibility but 180 degrees for a linear. That's it. All right. Ooh, this is a challenging one. I think I've seen this before. See if I can do it. Since it's not worked out for us, let's see if I can get this one done. Okay. This is where we start. Ki HNO3 yields KNO3 NO I2 and water. Okay. My guess is, no guess, this is a redox reaction. That's a -1, and this one's a 0. We did redox, didn't we?
So yeah.
Yeah. Wait a minute. No, we didn't. That must be the second semester. Hold on. Yeah, electrochemistry. Okay. This one might not be a fair question. We should be able to balance it with the budget method, but it's difficult because it's a redox reaction. We're moving electrons too. I'm gonna try to do it budget method because I haven't introduced the half reaction method yet. There's no guarantee. I mean, we have a nitrate here and a nitrate here, but we also have nitrogen split out of that over here. That's a problem. And then we have oxygen here going there, there, and there. So that can present a real problem. Let's see how far along we can get with the budget method. If I run into a snag, then I'll ditch it. All right, K, I, H, N, and O, right? 2, 3, 4, 5. Yep. This is 1K, this is 1I, this is 1H, 1N, and 3 O's. This is 1K, iodine, 2 iodines, right? Hydrogens, 2. Yep. Nitrogens, 1, 2. And oxygens, 3, 4, 5. Now let's see if I got that right. 1, 2, 3, 4, 7. 2, 3, 4, 7. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12. 1, 3, 4, 5, 6, 7, 12. Okay, so everybody's accounted for. All right, we have iodine as an element, so we could save that one till last. That might help some. And how about potassium? Well, potassium's already equal, so we got to go to something else. Hydrogen, nitrogen, or oxygen. All right. The problem with nitrogen is it occurs in 2 different places, and oxygen occurs in 3 different places. So we can try nitrogen and see if we've got 2 on that side. What if we put a 2 here? That gives it 2 there. That makes 2 nitrogens. That makes 2 hydrogens and 6 oxygens. Okay. So we're kind of messed up there. But if no, iodine's not going to work. We need 2 iodines on this side. Okay. So that's okay. But now we need 2 here. And now we need 2 here. Right. So that the iodines are okay, potassiums are okay. We've messed with the nitrogens and the oxygens. So that's 2, 3 nitrogens. And 6, 7, 8, 9 oxygens. So if we increase, if we make this side even, right? If we make this side even by putting 2 here, right? That makes 2 and 2 is 4. All right, let's take care of the 6, 7, 8, 9. That's 9. Wait a minute. 6, 7, 8. I miscounted before. 6. This should have been 8. Now it's 9. All right, it should have been 8. Now it's 9. And if we balance then the nitrogens over here, that means we would need 4 here. Right, so that would be 4 nitrogens. That would be 8 hydrogens. Okay. No. What am I thinking of? It would be 4 hydrogens. Duh. 4 hydrogens, 4 nitrogens, and 12 oxygens. Okay. All right. Hydrogens on this side. So if we want put a 2 here, then we get 4 hydrogens here, that gives us 2 more oxygens. 2, 4, and 6 is 10. All right. Oh, we do have 2 over here like that. All right. Let's see. We're stuck with oxygens. How do we get around oxygens? If we double up oxygens and add 2 more, that will get us here, rather than doing these oxygens. If we make that one 4, now we have 12 oxygens and 8 hydrogens, right? Yeah, 8 hydrogens. Now we got to have 8 hydrogens on this side. So this would be 8 hydrogens on this side. And that would also be 8 nitrogens and 24 oxygens. So we're messed up again. Okay, instead of messing with those oxygens, what about these oxygens? How would we get 24 out of that? Well, it occurs in several different places. So this was 2 and 4 is 6. So we've already got 6 taken care of. 6 from 24 is 18. So if we had 6 times 3, right, that would be 18 plus 2 is 20 plus 4 is 24. But this also makes 6, 7, 8 nitrogens. Oh, that's good. 6 potassiums. Okay. And we counted the oxygens already. Okay. So we need 6 potassiums on this side, right? That makes 6 iodines. So if we put a 3 here, that's 6 iodines. And that makes 6 iodines here. Oh, okay. 6, 8, 6, 2, 3, 4. That's balanced. But it was really haphazard, right? Just a lot of guesswork. Have we talked about movement of electrons in a balanced equation, in balancing an equation? Do you recall? Okay. Because it would be a whole lot easier if we balanced the electrons first, and then we went to the budget method. Let's see, how many more do we have? 48, 49, 48, 49. That's another 10 or 15 minutes there. And we're at 2 o'clock. And we're already into the lab. And lab runs till where is it? Here it is. 3:50. Okay, we got time to do it. I just want to demonstrate how much easier it is if we do the electrons first. And it's not necessarily something that you need to remember, but I think it would be useful, especially since you're going to take the second semester. Then you'll see this again. All right. First thing we have to do is say, all right, assign what we call oxidation states. In other words, it's kind of like charge, but it's really a bookkeeping scheme. Right? Oxygens are always -2, hydrogens are +1. Elements in their most stable form are 0. So this is a -2, that means this is a +2, right? We have to balance the charges. This would be a -2, This would be a +1 because it's an alkali metal. Right, that's familiar. This is a -6, and this is a +1. So that's a -5. That means this has to be a +5. Okay. This is a -2. That's the same thing, +5. Right? Because this one's +1. And this is -1 +1. Okay. Now we need to track how do the electrons move. Well, one species loses electrons and another species gains electrons, and they're always the same number. So this iodine goes from a -1 to a 0. That means it had to lose 1 electron for each iodine. Right? Okay, so I draw a tie line here. This means there was a loss of 1 electron for each iodine. I'll come back to that in a minute. That means somebody had to gain electrons. Hydrogen didn't gain any, it's the same, both sides. Potassium's the same. Nitrogen went from here to here the same, but it went from here to here different. So one of those, whatever nitrogen went that far, it went and gained 3 electrons. Right? 3 negatives plus a +5 is +2. Okay, so it gained 3 electrons for each nitrogen. Okay, all right. If we fix, well, how are we going to get equal numbers of electrons gained and lost? If it's only 1 electron here and 3 there, then we need 3 up here, but that doesn't work because you've got 2 there. So here's what I do. I say, let's balance times 2 iodines equals 2 electrons. And let's balance it like this. Right? There are 2 iodines. Now, in order to balance 3 and 2, we want 6 total. So we're going to multiply by 3, and this one by 2. So what does that mean? That means whatever we did up here has to be multiplied by 3. So we put a 3 here. That makes this a 6. Right? Okay. And on this one, we multiply by 2. So we went from here to there to there. That's 6 electrons. 6 electrons. Okay. Now we've got a starting point where we balance the electrons, 6 and 6. Okay. Now I'm going to go, this is my new starting position for using the budget method. Okay. Now we're going to tally things again. Potassium, iodine, hydrogens, nitrogens, and oxygens. Okay, now we're starting off with 6 potassium, 6 iodines, 2 hydrogens, and 2 nitrogens, and 6 oxygens. And on this side, we're starting off with 1 potassium. Yeah, starting off with 1 potassium, iodines, 6 iodines, and hydrogens, 2, and nitrogens, 1, 2, 3, and oxygens, 3, 4, 5, 6. Okay. Now, if I match the potassiums, I want 6 potassiums on this side. That changes the nitrogens. So I have 6 plus 2 is 8 nitrogens. Okay. And we've got 18, 20, 21 oxygens. Right? Okay. Now, How about nitrogens on this side? Well, we need 8. We only got one location here. So 8 in front of this one, right? So that gives you 8 nitrogens, 8 hydrogens, right? And 24 oxygens. There. Okay, now we need to do oxygens. So in order to get 24, we need 3 more oxygens somehow. Okay, let's see, we got 18, 19, 20, 21. We need 3 more oxygens over here. So that makes 24, but we've changed the hydrogens. So that's 6 hydrogens, right? Wait a minute. Yeah, that's 6 hydrogens. We need 8 hydrogens. So if I put a 4 here, that makes, maybe that was the wrong coefficient. Oxygens. I need 3 more oxygens. Wait a minute, 18, 19, 20. Oh, I do need 4. Yeah. 18, 19, 20, 24. There we go. So that means we actually have 8 hydrogens. Okay, now it's balanced. That was a little bit easier, I think, doing it that way. But it's not something you're going to be held responsible for. Not this semester. We'll get to it second semester. All right, that looks like a good extra credit problem there. Okay, number 48. Okay, next to the last one. One of the major commercial uses of sulfuric acid is production of phosphoric acid from calcium sulfate. Yeah, that's true. The phosphoric acid is used for fertilizer. The reaction is calcium phosphate plus sulfuric acid that yields calcium sulfate plus H3PO4. What mass of concentrated H2SO4 must be used to react completely with 100 grams of calcium phosphate? So our balanced equation, this is a stoichiometry problem. We've got Ca3PO4 and H2SO4 yields 3 calcium sulfate. Calcium sulfate with a couple of waters on it is gypsum. Remember that? Yeah. So, and that's one of the major byproducts from this whole process. So the phosphate industry takes that product and they market it. They recover some of their expenses by selling their calcium sulfate. Of course, they get more for the phosphate than they do for the gypsum, but it does offset some of the cost. All right, so that's balanced. Okay, what mass of concentrated react with 100 grams of calcium phosphate? We got 100 0 grams of calcium phosphate, and we want to know the mass of concentrated here. We want to know the grams of 98% by mass of that to completely react with that product. So remember, you can't go anywhere in a balanced equation unless you have moles. So we got to convert that to moles. Okay. We need to know the molar mass of calcium phosphate. Let's see, 3 times calcium is 4008. Okay, One phosphorus is 3097. And 4 oxygens is 64. So that's the molar mass of calcium phosphate. 40.08 times 30.97 plus 60 plus 215.21. Okay, so that's divided into 100. That's 0.464466 moles of calcium phosphate. Okay. Now, ratio is 3 to 1. So that many moles we can convert to calcium phosphate down here and sulfuric acid up here. 3 to 1. Now this is pure sulfuric acid. We haven't introduced this purity factor yet. So that's 1.394 moles. Excuse me. Yeah, moles of sulfuric acid. Now we need mass of sulfuric acid. Because this is in terms of mass. So we can't use the purity factor until we get mass. Okay, so sulfuric acid would be 2.02 for the hydrogens, and sulfur is 3207. Yeah, 32.07. There's only one of them, and then 4 times 16 again is 64. Okay, so 64, 32.07, and 2.02. That's 9809. Times 1 point, yeah. So let's see, I got 13.7 grams of pure sulfuric acid. The purity for this, and what we need is this would be pure, but since we're reduced by 2%, we need to end up with a value greater than 13.7. That helps me keep things oriented, so I know this is for every 98 grams pure, we have 100 grams of what would we say? 100 grams of 98%. Okay, that's what we're saying. This is pure, so we have to take that, divide it into it times 100. And that's, let's see, rounded off 13.95 grams of 98%, or something close to that. Let's see, scroll down, 96.8. Wait a minute. I make a mistake. I did make a mistake. A huge mistake. Somewhere. Okay, that's good. Let's see. 100. 3 times 40.08. Wait a minute. 100 grams. Yeah, 100 grams. Then 40.08. And oh. No wonder it's messed up. That's 2. And this is 8. So that's 128. And this value is going to be, I wonder it didn't work. This value is going to be 310.8. 310.18. That changes this value. I'm just going to save time. 322. Okay. This one is going to be 967. Yeah. 0.967. And that's 98.0. Okay. That's good for now. This is going to be different. It's going to be 98.967. Yeah. 9484. Okay. Now divided by 0.98 is 96. 96.8. Yeah, that's bigger than this one. Not by much, by 2%. A little mistake can get you. Ruin your whole day. And the last one. Number 49. Okay, characteristic odor of pineapple is due to ethyl butanoate, compound containing carbon, hydrogen, oxygen only. Okay. Combustion of 2.78 grams forms 6.32 grams of carbon dioxide, 2.58 grams of water. Properties of the compound suggest that the molar mass should be between 100 and 150. Okay. The end result of this is going to be based upon the empirical formula, right? The simplest whole number ratio. And once we get that, it's carbon, hydrogen, and oxygen, something in here, and then a factor here that gives us a weight that's between 100 and 150 grams per mole. Okay, so what we have to do first is find out the number of grams of each of the elements. Right? That's the first step. So we're told that we get 6.32 grams of carbon dioxide, 6.32 grams of carbon dioxide, which is CO2, and we need to convert that into carbon. Right? So we need the molar mass of CO2 versus carbon. Right? Carbon dioxide would be 32 plus that, or 44. So that's going to give us the mass of the carbon. Okay. 6.32. Yep. 12.01 and 44.01. So that's 1.725 grams of carbon. All right. Then hydrogen is derived from water, 2.58 grams of water. And the ratio here, we want to get hydrogen out of that. So we got two hydrogens, which is 2.02 grams. And then the ratio of the whole thing is 18.02 grams for the total. That's the total water. And this is hydrogen in that molecule. So 2.58, 2.02 divided by 18.02. And that's 0.289 grams of hydrogen. Okay. So how about oxygen? Well, we couldn't analyze oxygen directly because we were using oxygen to combust the sample. So oxygen has to be determined by default, by difference. So if we have 2.78 grams of ethyl butanoate, and we know this is carbon of it and this is hydrogen of it, then the total 2.78. 2.78. If we subtract that and that from it, we should get oxygen. That's what's left over. 2.78. And minus that. And minus that. So I get 0.766 grams of oxygen. Okay. All right. Now we have mass for each one. We can convert these into moles. Grams on the bottom, moles on the top. Okay. For each mole, carbon is 12.01, hydrogen is 1.01, and oxygen is 16. See, I've already got that one in there, so I'm going to just divide it by 16. And that's 0.0479 moles. Okay. 0.289 divided by 1.01 is 286, 0.286 moles of hydrogen. And the last one, 1.725 divided by 12.01 is 1.436 moles. Okay, so we're working our way toward whole number ratios. So I divide through by the smallest one. That's this one. Hope I'm on track here. So this will be divided by 0.0479. That's equal to 1. This one divided by 0.0479. Split that and 0.0479. This is 5.97. And this one divided by 0.0479. This one is 3.00. This one is very close to 6. That was 3 and that was 1. So our empirical formula is C3, H6, and O1. The empirical weight is what we're after so that we can compare it to the molecular weight. So this is 3 times 12.01 and 6 times 1.01 and then 1 times 16. Add those together. So this is 58.09 grams per mole. All right. If we multiply this by 1, that's 5809. That's not in the middle of 100 to 150. If we multiply it by 2 times 2, then we get 1, 8, 16, 1, 10, 11, 116.18. That's in the middle. If we went another one, that would be 160, 170, and that'd be over our range. So N equals 2. And our molecular formula is C6H12O2. I think that's the last one. Yep. Let's see, what do we got here? Useful information. Okay, we're good. Yep. And that means that Thursday will be a tutorial day.
Okay.
And I'll be zoomed in case you need any help let me be sure. Thursday. I never know doctor's appointments. And they're not just my appointments. Let's see, Thursday. Yep, we're good. Yeah, I'll be zoomed in for the class, and then I'll zoom in office hours afterwards. So if you can't, if you think of something after the class is over, go to my office hour connection, to my link, and find me there. Okay, we're done for the day.